Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about the passing of AC through series LR circuit and also series RC circuit. This topic is meant for class 12 students of CBSE, ISE and different state boards. The topic covered here will also be found useful for various competitive exams like NEET and JEE Mains. The complete note of the topic is given here for your convenience. I hope you enjoy going through it. Now let us come to the topic. First, we consider the flow of AC through a resistor and an inductor, which is commonly known as series LR circuit. So in this figure 1, we have an inductor of inductance L and a resistor of resistance R connected in series, across which we have an alternating EMF E equal to E naught sine omega t applied. And we have to find out the expression for the instantaneous current I. Since the EMF and hence the current varies with time, there is a production of back EMF across the inductor. We represent it by a small e, and the magnitude of this is given by L times di upon dt, where di upon dt is the rate of change of current. That there is the production of a back EMF across an inductor when an alternating current passes through it has been discussed in an earlier lecture. The effective EMF in the circuit is equal to E minus L di upon dt. E is the applied EMF and this is the back EMF produced across the ends of the inductor. So we apply the Ohm's law now. So current in the circuit is the effective EMF upon the resistance. So I equal to E minus L di upon dt upon R. Note that an ideal inductor has no ohmic resistance and therefore the total resistance in the circuit is simply R. Clear? So E minus L di upon dt is I into R, or E naught sin omega t is IR plus L di upon dt. We have earlier seen that the current through the resistor is in phase with the applied EMF, whereas through the inductor it lags behind the applied EMF by pi by 2. Therefore, the current through the series LR circuit will neither be in phase nor lag behind the applied EMF by pi by 2, but will lag behind the voltage by some angle phi, where phi lies between 0 and pi by 2. So we express the current I through the LR circuit as I equal to I naught sine omega t minus phi, where phi is the angle by which the current through this circuit lags behind the applied EMF, and I naught is the peak value of the current. Okay. So from this equation 2, we find the value of di upon dt. So di upon dt is I naught omega cos omega t minus phi. Put the value of I and di upon dt from equation 2 and 3 in equation 1. What do we get? We get E naught sine omega t is R I naught sine omega t minus phi plus omega L I naught cos omega t minus phi. Okay. So this is for IR. Okay. And this is for L di upon dt. Clear? So this equation 4 is true for all times, and therefore we take omega t equal to 0. So equation 4 gives you E naught into 0, because sine omega t is sine 0 and sine 0 is 0. So left hand side of the equation is 0. This is R I naught sine minus phi plus omega L I naught cos minus phi, because omega t is 0 here already. So sine minus phi is minus sine phi. We transfer it on the left hand side. So this is, and moreover, this I naught cancels with this I naught. So r sine phi is omega L cos phi. So this gives you tan phi is omega L upon r. ठीक है? So याद रखिए, if you know the value of tan phi, you can find the value of sine phi and cos phi. How? You remember this, that we have tan phi is P upon B. P is perpendicular, B is the base, and this is omega L upon R. Okay, and therefore H is root over B square plus P square equal to the square root of R square plus omega square L square. Okay, and therefore sine phi is P by H. So P is omega L upon H is R square plus omega square L square root over. Okay, this is what we have written here. Similarly, cos phi कितना हो जाएगा? Cos phi will be equal to R divided by R square plus omega square L square का root over. So this is written here. Sin phi is this and cos phi is this. Okay. Now, so assume that omega t is pi by 2. Then equation 4 gives you E naught is I naught R cos phi plus omega L I naught sin phi. Okay. So from equation 6, we have R equal to root over R square plus omega square L square cos phi, and omega L is root over R square plus omega square L square sin phi. This comes from equation 6. Okay. Put these values in this expression. For the R and omega L. So what do you get? We get E naught equal to I naught within bracket R square plus omega square L square cos square phi plus R square plus omega square L square root over sin square phi. So this term is common. So I take it outside the bracket. So this gives you E naught equal to I naught root over R square plus omega square L square cos square phi plus sin square phi. So this term is equal to 1. Okay. So this is simply equal to I naught root over R square plus omega square L square. So the maximum value of current is E naught upon root over R square plus omega square L square. Referring to equation 2, we find that the instantaneous current I is expressed as I equal to, this is for I naught sine omega t minus phi. Okay, so this is for your I naught from this expression where tan phi is omega L upon R. Clear? इस इक्वेशन में ये पार्ट जो है, दिस इज नथिंग बट EMF. ठीक है, दिस इज योर EMF. On the left side, we have the current, and therefore the denominator must represent what? It must represent the impedance or the resistance offered by the circuit to the flow of alternating current. So we compare equation 7 with Ohm's law. We find that the effective resistance Z of the circuit shown in figure 1 is Z equal to root over R square plus omega square L square. This is known as impedance. The reciprocal of the impedance is called admittance. The ratio of the EMF to current strength in the circuit at any instant is given by E equal to E naught sine omega t upon I naught sine omega t minus phi. We see from equation 9 here that the ratio E upon I is not a constant, but is a function of time. The instantaneous value of E and I therefore do not obey Ohm's law. Ohm's law में क्या होता है? E upon I constant रहता है. यहाँ हम देख रहे हैं कि टाइम का फंक्शन है, so this is not a constant. Therefore, the current flow through AC circuit containing L and R does not obey Ohm's law. The current and voltage waveforms when an alternating EMF is applied across a series LR circuit is shown in figure 2 with its vector diagram. We see that the current lags behind the applied EMF by certain angle. Let us now see how the vector diagram is drawn. The applied EMF has to overcome the potential drop IR across the resistor which is in phase with the current. यहाँ पहले यदि देख चुके हैं when an alternating current flows through a resistance, an ohmic resistance, then the current and the voltage are in phase with each other. So the applied EMF has first to overcome the potential drop IR across the resistor which is in phase with the current. And second, it has to overcome the back EMF LdI upon dt across the inductor which lags behind the current by 90 degree. And therefore, the applied EMF which must be opposite to this back EMF must therefore lead the current by 90 degree. करंट से बैक ईएमएफ 90 डिग्री पीछे है. हम चाहते हैं कि करंट फ्लो करे, तो क्या करना होगा? जो बैक इधर हमारा करंट है, इधर हमारा बैक ईएमएफ है. ठीक है, हम चाहते हैं इसके क्रॉस, इसके थ्रू करंट फ्लो करे, तो जो अप्लाइड ईएमएफ होगा दिस मस्ट बी अपोजिट टू दिस बैक ईएमएफ. ठीक है, ये इधर होना चाहिए अप्लाइड, है कि नहीं? सो द अप्लाइड ईएमएफ must be ahead of the current by 90 डिग्री. मान लीजिए कि दो कंपोनेंट जो हैं अप्लाइड ईएमएफ के, उसको हम रिप्रेजेंट कर रहे हैं दो म्यूचुअली परपेंडिकुलर स्ट्रेट लाइन OA और OB से इन मैग्नीट्यूड एंड डायरेक्शन. स्ट्रेट लाइन OA जो है दिस रिप्रेजेंट्स द वोल्टेज दैट अपीयर्स अक्रॉस द रेजिस्टेंस एंड द स्ट्रेट लाइन OB रिप्रेजेंट्स the potential that appears across the inductor. So with OA and OB as sides, we complete a rectangle OADB. Then the straight line OD represents the resultant of IR and I omega L in magnitude and direction. Because this OAD is a right angle triangle and this is hypotenuse, the length of this will be equal to I times root over R square plus omega square L square. ठीक है? If this is I omega L, this is also I omega L. And therefore, this is the resultant of these two. Okay? So from figure 3, we see that the effective applied EMF is represented in magnitude and direction by OD, which leads the current by an angle phi, where phi is given by tan phi is AD upon OA. AD is given by I omega L. OA is IR. I and I cancel out here. This is omega L upon R. And this is simply omega L is XL. And this is R. So this is simply XL upon R. This is what we have also represented or expressed in equation 5. The relation between the effective or RMS value of the applied EMF at any instant with the effective current is given by E equal to I times root over R square plus omega square L square, where this part is the impedance of the circuit containing resistor and an inductor in series. Okay? Thus, when an alternating EMF is applied to an inductive circuit, it may be supposed to be resolved into two components, IR and I omega L. The in-phase component, IR, is known as the power component, and the out-of-phase component, I omega L, is called the wattless component of the EMF because it does not supply any power to the circuit. So now we come to an example. An inductor of 0.2 Henry and a resistor of 10 ohm are connected in series to a 220 volt 50 Hz AC source. Find the current in the circuit and the angle by which the current lags behind the applied voltage. ठीक है, एक सर्किट है जिसमें 0.2 हेनरी का इंडक्टर लगा हुआ है और रेजिस्टर लगा हुआ है 10 ओम का. ये दोनों कनेक्टेड है सीरीज में. उसके अक्रॉस हम एक एसी सोर्स लगा रहे हैं 220 वोल्ट और 50 हर्ट्ज का. We have to find out the current in the circuit and the angle by which the current lags behind the applied voltage. So what is the impedance? Impedance of the RL circuit is given by Z equal to root over R square plus XL square. Put the respective values here. You get here value of Z as 64 ohm. So the current in the circuit is I equal to V upon Z. This is 220 volt upon Z is 64 ohm. So this is 3.44 ampere. The angle by which the current lags behind the voltage is given by phi equal to tan inverse omega L upon R. Tan inverse omega L का वैल्यू कितना होगा 20 पाई. देख लीजिए आप. R is 10 ohm. So this is tan inverse 6.286 and this gives you the value of the angle by which the current lags behind the voltage. The value can be found, the angle can be found using a log table. Okay? We now come to the flow of AC through a resistor and a capacitor, which is commonly known as RC circuit. So consider a series RC circuit across which we have an alternating EMF equal to E naught sine omega t applied. So this is the capacitor of capacitance C, this is the resistor of resistance R. Across this we have an EMF equal to E naught sine omega t applied. Okay? So let I be the current at any moment and Q be the instantaneous charge on the plates of the capacitor. Apply the Kirchhoff's law. Then we have E equal to E naught sine omega t will be equal to the drop across the resistor, and this is I into R, where I is the current at any moment, plus Q upon C, where Q is the charge on the plates of the capacitor. So this is in effect the potential across the capacitor plates. We know that the current through a resistor is in phase with the applied voltage, and that through a capacitor leads the applied voltage by 90 degree. Therefore, when a current flows through a series RC circuit, the current will neither be in phase nor lead the applied voltage by 90, but will lead the applied voltage by some angle phi, where phi will lie between 0 and pi by 2. So we assume that the current is I equal to I naught sine omega t plus phi. The values of the peak current I naught and the phase angle phi are to be determined. We have the current rate of flow of charge. So I equal to dq upon dt. So q will be equal to integral of dq. This will be equal to I into dt from this expression. Put the value of I here. So this is I naught sine omega t plus phi dt. Integrate this. This is q equal to minus I naught upon omega cos omega t plus phi. Okay? Substitute for I and q from equation 11 and 12 in equation 10. What do you get? You get E naught sine omega t is equal to r I naught sine omega t plus phi minus I naught by omega c cos omega t plus phi. This is your current I. Okay. So therefore, this term from here to here, this is IR, the potential drop across the resistor. And this term nothing but potential across the plates of the capacitor. So this equation 13 is true for all values of time. So put omega t equal to 0. Then equation 13 gives you on the left side, this becomes 0 because omega t 0, sine 0 is 0. So left side is 0. So this is 0 equal to r I naught sine phi because omega t is 0 here minus I naught by omega c cos phi because this omega t is 0 here. So we have r sine phi is 1 upon omega c cos phi because in this equation you show that this I naught cancel from both sides. So we have tan phi is sine phi by cos phi. So this is 1 upon omega c upon r. So this is written as xc upon r, where xc is equal to 1 upon omega c is the capacitive reactance of the capacitor. जैसे इंडक्टिव रिएक्टेंस होता है इंडक्टर का, एक्सेल से रिप्रेजेंट करते हैं उसको, उसी तरीके से हमारे पास कैपेसिटर का रिएक्टेंस है, उसको बोलते हैं कैपेसिटिव रिएक्टेंस. इसको रिप्रेजेंट करते हैं एक्सी से, वेयर एक्सी इज इक्वल टू 1 अपॉन ओमेगा सी. So from this equation for tan phi, you can find the value of sin phi and cos phi. कैसे निकालते हैं ये मैंने आपको पहले बताया है. कैसे निकालते हैं देखिए, tan phi होता है आपका, हिंट कर देते हैं, आप देख लीजिएगा. tan phi is 1 upon omega c upon r. So this is your xc upon r, and tan phi is p upon b, perpendicular upon base, and therefore the hypotenuse will be equal to a square root of b square plus p square. Okay, so this is r square plus xc square. So from here you can find the value of sin phi. Sin phi is p by h. So this is xc upon root over r square plus xc square, and cos of phi is equal to r upon square root of r square plus xc square. Now take omega t is pi by 2. Then equation 13 gives you E naught sin omega t के बदले क्या लिखेंगे, sin pi by 2, and this gives you on the right side r I naught sin pi by 2 plus phi. For omega t we have written here pi by 2 minus I naught by omega c cos pi by 2 plus phi. Now sin pi by 2 is sin 90 is equal to 1. So this term gives you simply E naught. This is written here. Sin 90 plus phi is cos phi. So this is here cos phi. Okay. Minus I naught upon omega c cos 90 plus phi is minus sin phi. So this gives you here E naught is I naught r cos phi. This minus minus gives you plus here. Xc for 1 upon omega c, we have written xc here, xc sin phi. Now put the value of cos phi and sin phi in the next step. So E naught is I naught r times r upon root over r square plus xc square plus xc into xc upon a square root of r square plus xc square. So E naught is equal to I naught into within bracket r square upon root over r square plus xc square plus xc square upon root over r square plus xc square. You see that the denominator of the first term and the second term are the same, and therefore this gives you E naught equal to I naught into within bracket r square plus xc square upon root over r square plus xc square. So this gives you simply E naught equal to I naught into root over r square plus xc square. So from equation 16, I naught is equal to E naught upon a square root of r square plus xc square. We are now in a position to write the value of instantaneous value of current, which is given as I equal to I naught sine omega t plus phi. This we have seen earlier. So in this equation, put the value of I naught. So I naught is given by this expression. So I equal to E naught upon root over r square plus xc square sine omega t plus phi. Clear? So if you compare equation 17 with Ohm's law, we find that the total impedance of the series RC circuit is given by Z equal to root over R square plus XC square. The current and the voltage waveforms are shown in figure 5 together with the vector diagram. We see from figure 5 that the EMF lags behind the current. This is the curve for applied EMF, and this is the curve for the resulting current. Clear? We see that the EMF reaches its maximum value E naught. This is the position of E naught here, maximum value of the EMF. That the applied EMF reaches its maximum value after the current has reached its maximum value. So the EMF lags behind the current, or the current leads the applied EMF by certain angle phi. Okay? So this is all about the passing of AC through an LR circuit and a RC circuit. I hope you like this presentation. यदि आपको मेरा प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.